everywhere. Okay, it's sticky, it becomes crystalline. Okay? So the simplest carbohydrates are therefore the sugars that are these chains of which glucose is an example. And so they can either be aldehydes, as in the case of glucose, and when they're aldehydes, they're called aldoses. And they can also be ketones, in which case they're called ketoses. And when they're ketones, what has happened is the carbonyl has jumped one carbon down the line. In other words, the two terminal carbons, aldehyde and hydroxymethyl, just trade oxidation state formally. So these two carbons, this can be a carbonyl, in which case this one becomes CH2OH. Okay? So it's a redox, if you wish, a hydrogen transfer from one carbon to the other. In those cases, they're called ketoses. And so they can form dimers, trimers, and so forth by ether bridges, because we got all these OH functions, they're all secondary alcohols, and so they can make ether linkages. And as we shall see, even more importantly, because it's a hydroxyaldehyde, they can make acetyl linkages, which are particularly easy to cleave and to make. So what is the simplest sugar? The simplest sugars are these two here. One of them is an aldose, the other one is a ketose, 3-carbon sugar. The convention is to write the carbonyl as far to the top as you can. So in the case of aldehydes, obviously it's the top carbon. In the case of a ketose, it's in this case it's in the middle. But whatever, if you make a longer chain, you always extend down below. Okay? In the case of this guy here, this is a stereocenter, so this molecule is chiral, and this molecule by IUPAC would be called 2,3-dihydroxypropanal. It's got a long history. It's the simplest aldose. Its common name is glyceraldehyde. So this is an aldo triose, where tri stands for the number of carbons. So triose, 4 carbons is tetros, 5 carbons, pentose, and so on. The corresponding ketose, of course, is just simply dihydroxyacetone. So that's very, very simple picture. Once you extend the chain, you get more and more variety. Okay? Here's some important monosaccharides. Here's glucose again. And again, as I pointed out already on the model, 4 stereocenters. 4 stereocenters means you can have 2 to the 4, that is 16 stereoisomers, of which there are half of them are image and the other half is mirror image, but you still have 8 diastereomers. Okay? And that's by virtue of the fact that each one of these carbons can be either R or S. Okay? So if you look at one important ketose, this is fructose. Okay? Fructose is an isomer of glucose, simply formed from glucose formally by taking these 2 hydrogens away from this carbon and putting them on the CO double bond, and that gives you the carbonyl transposed isomer. Because having the carbonyl here kills the stereochemistry at this carbon, now we only have 3 stereocenters, meaning 2 to the 3 stereoisomers, 8 possible stereoisomers, 4 diastereomeric pairs of isomers. Another important one is ribose. Okay? That ribose is a pentose, and it's got 3 stereocenters, and they're the molecular models. Now, right off the bat, I won't ask you to memorize these names. Okay? The only thing one can expect you to do is actually use IUPAC nomenclature to name these, and that's very, very simple, because it's just polyhydroxy aldehydes or ketones. Okay? So glucose, as you know, is also known as dextrose. It's also blood sugar, grape sugar. Those of you into sports, sometimes people take glucose pills because it's an even more readily available form of sugar than table sugar. Table sugar, you have to hydrolyze the bond between glucose and fructose to liberate the 2 individual sugars for further metabolism. So table salt is this plus that linked by an ether bridge. And we'll see the structure towards the end. And so when you hydrolyze table sugar, you get 1 molecule of glucose, 1 molecule of fructose. Fructose, of course, is the sweetest natural sugar there is. Okay? And ribose, of course, exists in ribonucleic acids. Okay? So that's why that sugar is important. Now, you notice with all these stereocenters, it is very difficult to keep track of stereochemistry unless you use some kind of a stencil that simplifies the picture. And those stencils were part of Chapter 5. They're the so-called Fisher projections. So I want you to review Chapter 5 as it pertains to Fisher projections. If you remember some of it, I'll review them right here. Okay? So the Fisher projections are basically a flat stencil made across at each stereocenter. So for example here, where the center of this cross is a carbon, and by convention, the horizontal lines are essentially wedged lines that come towards you, and the vertical lines go away. So the way they're constructed on a piece of paper is that if you put yourself into the position of this young lady here, into looking up, sitting in the plane of the board, looking up to this molecule here, you will notice that these 2 carbons come towards you. And it's always useful to actually, there's a little cartoon in Chapter 5, to, in your mind, grab those 2 carbons. Because once you grab any 2 carbons, in this case the 2 that come towards you, the other 2, or any 2 atoms, the other 2 substituents fall into place. Because one of them will be up to the back of you, and the other one will be down to the back of you. So if you grab this molecule like this, bromine will be up to the back of the center carbon, and the hydrogen will be down. And so here we're looking at this lady. Notice this we're looking, I don't know, from the top. Okay, this is a flower, not a brain tumor, and she looks up there. Okay, so you don't see the eyes. And so what she sees is this: okay? Wedged lines like this, and dashed lines for the vertical lines. And this is then translated simply into a cross. Okay? So when you see this cross, that's what it is. Now, these Fisher projections at each center can be readily interconverted without changing the absolute stereochemistry by double exchanges. Okay? Or you can also do 180-degree turns. I would advise against that. Things get muddled. But if you do double exchanges, you get the same enantiomer. If you do just a single exchange, you get the opposite stereochemistry. All right, so how does this translate into the simple sugar? Here it is. Here's the stencil. Okay, so we have the aldehyde on top, and these 2 guys are now wedged lines for this enantiomer of 2,3-dihydroxypropanal, also known as glyceraldehyde. This guy is dextrorotatory plus 8.7. Now, those of you who are going on in the biofields will often see the term D sugar instead of R and S. D is really a terrible, it's historical, terrible name. It comes from the original name for the dextrorotatory enantiomer of glyceraldehyde. So early sugar chemists had both image and mirror image. Okay? That's the levorotatory that rotates plain polarized light exactly the opposite direction. They had both compounds, but they didn't know which one's which, because there was no way in those days to determine absolute stereochemistry. This was only possible much later in the 40s and afterwards when X-ray crystallography became available, where you literally saw a photograph of the molecule. Okay? So at the time, they called it D because it was dextrorotatory, and 50-50 chance of guessing right. They just guessed at the structure. They just said, okay, we just give it that structure. And if we turn out to be wrong, then we just have to reassign everything derived from it. But they were lucky. They assigned the right stereochemistry by just giving it that. And the stereochemistry is OH to the right in this Fischer stencil, meaning that the mirror image, of course, is OH now to the left. And so this is called D-glyceraldehyde. And all the sugars in which the lowest, most chiral carbon has the OH to the right are called D sugars. Everything else can be left, right, all kinds of possible stereo combinations as long as the lowest carbon has the OH to the right. We'll see that in a minute. And the D sugars derived ultimately from D-glyceraldehyde are mostly the natural sugars. Most natural sugars have the lowest chiral carbon in the Fischer projection with the aldehyde or ketone on top, furthest most to the top, have the OH to the right. So here's how we designate D and L sugar. Here's a sugar, okay, it's an aldose, an aldehyde on top, and we have OHs and all kinds of stereocenters, and you have to come to the lowest carbon, the highest number stereocenter, highest number because it's furthest away from the aldehyde functional group. If that OH is to the right, then it's called a D sugar. In this case, a D aldose, okay? Regardless of whether this OH is to the right, left, okay? It doesn't matter. Similarly for the ketoses, if that sugar is to the left, if the OH is to the left and the lowest stereocenter is called L, and that would be an L ketose. So D aldose, L aldose, or D ketose, L ketose. It's what happens at the furthermost hydroxy function. So in terms of stereochemical relationships, just a simple example, a tetrose, okay? This one's called erythrose, as it happens. We have two stereocenters that can either be RR or SS. That would be image and mirror image. And in that case, the two OHs are to the right, as it turns out. And then, of course, the mirror image has the two OHs to the left. So these are two enantiomers. But you can draw another diastereomer where instead of having RR and therefore as a mirror image SS, you have RS or SR. Okay? And so here is the SR-RS combination. Okay? So this is a different compound from that one. Okay? It's a different stereochemical arrangement. It's related to cis and trans and cyclic analogs of structures like that. So these are two different compounds, but in the enantiomers, of course, are the same. They're just image and mirror image, and they differ only by the sign of rotation of plane polarized light. Otherwise, NMR is the same, melting point is the same, infrared spectrum is the same, and so on. But among the diastereomers, the NMRs are different, and the IR is different, and the melting points are different. Okay, and that then gives you the family of the aldoses and the ketoses. And again, I wanted to stress, I'm just showing it to you to give you a feel for the simplification that is imparted by using Fischer projections. Okay? Because we have a nice stencil, and then it just becomes an exercise in permutations on where you put the OH functions. And I'm giving you just the D-aldoses because most of those are the ones that are naturally occurring. With some exceptions, actually, I've spliced in the exceptions or specifics for the individuals. So they're all derived formally from D-glyceraldehyde, okay? The smallest aldose, okay? Aldotriose. So when you add another stereocenter, then you have 4 carbons, 2 stereocenters, we just did that, and so there's one diastereomer, and there's the other diastereomer. And notice that the OH at the highest number stereocenter is to the right, and that's why it's called D. This one is to the right, that's why it's called D. So in this family of the D-aldoses, it's just one image of all these molecules. The mirror image would be all the L-aldoses, okay? And they are lesser frequented in nature. So I'm basically splitting the number of stereoisomers in 2 halves. I'm just looking at one enantiomeric pair. So if you add another stereocenter, then we have 4 diastereomers. And the way to construct them is to just do an exercise of permutation. So you can start with this one, which happens to be ribose, all OHs to the right. And then you do left, right, that's arabinose. And then you can do right, left, and then left, right. Okay? That's all the possible permutations. So you see, it's kind of simple to arrive at what you have. These are all the naturally occurring there. D-lysose is rather a rare molecule. This one is at the L form is actually more common than the D form. So where, in other words, the mirror image of that is actually more common in nature than the D form. And then when you have 6 carbons, we have 4 stereocenters. And if you go through all the permutations, you arrive at 8 possible diastereomers. Okay? This guy, allose, is rather rare. Altrose is actually an unnatural. D-altrose is unnatural. It's mainly made in the laboratory. Okay? But there's glucose. And glucose, notice, in this Fischer stencil is right, left. Okay? Again, you don't need to memorize these in exams. I'll give you stencils. I'll give you names, except IUPAC names. If I'm asking for the IUPAC name of sugar, you should be able to do that. But otherwise, I'm giving you the stencils and everything. So I want you to do chemistry rather than be bogged down with details. So there's glucose. Mannose, notice, looks like glucose, except this stereocenter. This stereocenter is inverted. OH up on top here is now to the left, and mannose is to the right in glucose. Gulose is rare. D-idose is actually unnatural enantiomer. Galactose you may have heard of, so that's right, left. Talose is also unnatural. So fortunately, nature stops here, essentially. There are some larger, longer chain sugars, but those are the major sugars that are out there. So nature limits itself to a certain set, and even within this complete set presented here, it actually only picks a few that it uses extensively. And the reason for that is that it's got plenty of possibilities of making disaccharides and trisaccharides, because you can make ether linkages to the aldehyde carbon from another sugar via acetal formation and hemiacetal formation, and you can make ether bridges here, and here. And so if you add up all the combination, just to make a dimer of glucose, in fact, gives you a large number of possible arrangements that you can assume. So these are the aldoses, and then the corresponding ketoses are shown here, and because the ketoses have a carbonyl, they all have 1 stereocenter less, so that family is actually smaller. And so we start with the smallest one, dihydroxypropanone or dihydroxyacetone. You add 1 stereocenter, that's this guy, and again, D means the OH is to the right, and then you add a second stereocenter, and again we have the right, left combination. These are these two, and then you add another carbon, and that has 3 stereocenters, 4 possible diastereomers. Here's fructose. Fructose is left, right. Sorbose you may have heard of, right, left. Tagatose, it's in fruit, lots of fruits. It's left, right. And then again, nature stops here because that's enough to do. In fact, glucose, and we'll see on Thursday why, is by far the dominant isomer that's used in nature, and nature just stitches it up in various ways to make disaccharides, and then polymers. So starch, for example, is a polyglucose structure. We'll see that on Thursday. Thank you.